Hello everyone, I'm Eugène Freyssinet. Welcome to our show Ask Eugène, when we unravel the mysteries of technologies in a clear and accessible way. Today, my friend Oscar, expert in design of structures in seismic zones, is taking the lead. He'll be guiding you to a key concept in building safety, seismic isolation.
Hello, my name is Oscar. Thanks Eugene for inviting me. Here we talk about structures in a simple way. In the next series of videos, we will talk about seismic isolation. We will review how these systems are conceived and things that must be taken into account using a minimal mathematical knowledge. So let's begin. Are you ready? Seismic isolation is a technique through which the behavior of a rigid structure under high seismic force can be changed, transforming it into a more flexible structure, developing less force on its components and therefore making it safer and more economical. Additionally, it does not require an interruption of operation as can be seen in the video. Notice that while the building without isolation shakes completely, as it is subject to high seismic force, the isolation build moves much less under the same conditions. All the contents in the building are safe and represented by the small car inside the building. The magic is done by the small flexible element between the base of the building and the foundation, or in this case, the ball bearings that act as isolators. The devices change completely the way the building moves, making the build shake less. This is achieved because the isolator changes the natural period of T of the structure. But what is the natural period of a structure? How does something so simple make buildings safer? Every structure has a structural period, which is simply the time that it takes for a structure to complete one full cycle when undergoing free vibration. All structures have their own period depending on how rigid they are and how much mass they have. It is very common for low-rise buildings to have a very short period, medium-sized structures to have a higher period, and tall structures to have a much higher period than the rest. Imagine a little girl on a swing being pushed from behind by her father. If the father synchronizes his movement and waits for the right moment when the girl reaches her highest point to push her again, it can be said that the father and the girl are synchronized. As a result, the amplitude of the girl's movement will increase more and more, and the tension in the rope will grow greater each time. However, if the father is blindfolded and moves his arms forward in attempt to push the gear. Sometimes he will push her, and other times he will stop her. This means there will not be synchronization, and therefore the movement will not be amplified, nor will the tension in the rope increase. In this scenario, the building is represented by the gear, and the ground movement is represented by the father. The same phenomena occurs between buildings and the ground when their movements synchronize. When an earthquake occurs, just like in the example of the gear on the swing, the ground tends to push structures with a certain ground period. If the ground period and the structure's period synchronize, the result will be an amplification of the building's displacements, and the force within the building will grow larger and larger. If the ground period is longer, it will affect mid-rise structures, and if it's even longer, it will affect tall buildings the most. In the following video, observe how by moving the board that represent the ground movement, when the ground movement is very fast, the structures with shorter periods are the ones that move the most, while the medium and tall ones barely move. The same happens when the board's movement becomes slightly faster. The medium-heavy structure is the one that gets excited, while the other two move less. Finally, when the board moves slowly on the board representing the ground motion of a soft soil, the tallest structure is the one that is excited, while the other two barely moves. Now, let's check what a damping concept is with the next example. As you can see, we have two structures with the same condition, height and mass. When we move the board, they moves with almost the same period. If we add an element capable of representing damping, such as a friction element or a piece of paper, we can observe how these elements with similar periods slow down to varying degrees, with one element not as quickly and with the other much more quickly. If we know that we are in a seismic zone where the earthquake motion will excite short period structures, and we also know that our structure have a short period, we can deliberately change the structure's period to a much higher one, where the acceleration are significantly lower by using an isolation device. This allows a structure that naturally has a short period to behave like a long period structure, where we know it will experience less excitation and the force in its member will be much smaller. Thanks for watching, and we will see you in the next episode where we will cover the basic principles of isolation systems.
Thank you, Oscar, for this very interesting and clear explanation. If you want to know more, don't hesitate to go on our website, freyssinet.com. Bye bye, everyone, and see you for the next episode.